There are billions of stars in this galaxy called the Milky Way. Our star, the Sun, provides Earth organisms the energy to live and thrive. Around our Sun circle the many planets of our solar system. And many as they are, the planets of our solar system are only a fraction of the mass of our Sun. And our Sun is a relatively small star in the universal scale. I'm Larry Ross, Director of Space Programs at the NASA Lewis Research Center in Cleveland, Ohio, and I'm your host for a series of 13 programs about the solar system. During the series, Journey Through the Solar System, we'll closely examine our corner of the universe, beginning at the Sun and moving outward to Mercury, Venus, Earth, the Moon, Jupiter, Saturn, and beyond. Let's begin with the Sun. Inside, its temperature could be as high as 25 million degrees. Pressures are estimated at 1 trillion pounds per square inch. Not many years ago, man knew little about the Sun. Now, from a motion picture called Partnership in Space, Mission Helios, we have a clip about the past.
Man has been fascinated by the Sun since the beginning. In ancient Britain, the Druids built a mysterious monument to it. In Egypt, the Sun was worshipped as a deity, and its passage from day to night was sanctified. The Mayans offered sacrifices to the Sun. For the Aztecs, it measured time. Some artists reproduced it in colorful stones and gold. Others captured its mysterious quality on canvas. Children see it as a smiling face. It is the source of bounty and, as in parts of Africa, an element of devastation. Early man brought the Sun down from the sky to within his reach. Modern man journeys upward to understand it. Still, it remains a mystery.
To many of the ancient peoples of Earth, the Sun was not the center of the solar system. Often, Earth was considered the center of the universe. An excerpt from the film called A View of the Sky explains these views.
First, we had to come out of the darkness and shed a world of mysteries and superstitious beliefs. First, we had to fight our way upwards to clarity and light, to take the position we thought belonged to us, the very center of creation. It was Claudius Ptolemaeus who devised the first complete system of the universe. Ptolemy, who lived in Alexandria around 200 AD, said this: "The Earth is the center of the universe. The Sun and the planets turn around it in circles. Beyond the planets lie the celestial sphere of stars, which also turns around the Earth." It is not surprising that Ptolemy should have placed the Earth, and with it himself, at the center of the universe. This was dictated to him by the Greek image of man. Greek love and respect for the human body and mind. The Greek knew that man was beautiful and that he was a hero, knew it beyond all doubt. That is why he created gods after his own image, and that is why he could conceive of only one place for himself in the universe, at the very hub. Nor is it surprising that Ptolemy's heavenly bodies should have moved in circles. Greek love for harmony is reflected by a love for geometric forms, and above all, for roundness. Nor were the Greeks content with just loving roundness. In typical Greek fashion, they systematized their instinct and promoted roundness to a principle of nature. Aristotle, the father of Greek physics, proclaimed the circle the perfect form, circular movement, the perfect movement. Since the planets were bodies of divine nature, they could move only in circles. This to the Greeks was so obvious that it became the supreme law of their astronomy. Ptolemy's contribution, of course, is far more than having applied Greek philosophy to the sky. His great achievement is having brought the essence of Greek thought and Greek culture into agreement with observation.
Today we know that the family of planets, asteroids, and comets circle the sun. We also know that our star is like a grain of sand on an infinite beach. There are so many stars that we cannot truly count them all. What is the model of the structure of our sun, this average-sized star? For that, and how we study the sun, let's go to the motion picture Universe, narrated by William Shatner.
Some small stars do not travel in the company of other stars. Our own sun is one of these. To the astronomer, the sun is a vast laboratory for the detailed study of a star's structure and energy. The vertical tower of the solar observatory supports a heliostat mirror which tracks the sun, gathers its rays, and reflects them down a light shaft that extends 300 feet below ground. At the end of the shaft, the rays are cast back to an observing room where minute-by-minute changes across the face of the sun are observed. Another mirror projects a light beam to a spectroscope, an instrument which splits the light into its component colors, a visible spectrum. The dark lines that cut across the spectrum band are produced by the radiation from the sun's interior shining through its atmosphere. Each line is the signature of a chemical element such as sodium, iron, calcium. It is this array of lines that forms the code which describes the properties and motion of a star. By narrowing the view of the sun to a single line of the spectrum, each level of the solar atmosphere can be photographed, and each reveals a remarkably different aspect. And with the addition of computer mapping and color processing that distinguishes levels of brightness, a detailed and multidimensional picture is obtained of a sun undergoing dramatic and turbulent change. The sun is a sphere of hot, seething gases and surges of radiation. Most of the light we get from the sun comes from the thin, bright layer which defines its visible edge, the photosphere. Above it, the chromosphere, a region of flaming outbursts of gas, extends through a transition zone to the thin outer atmosphere of the corona. Once thought to be a quiet layer of the solar atmosphere, the corona is now revealed to be a region of dramatic large-scale changes and unexpected turbulence, with temperatures reaching millions of degrees. Deep beneath the sun's atmospheric shell is the core, a violent nuclear furnace. Here, hydrogen is fused into helium, and in the process, some of the matter is converted into an enormous amount of energy. Radiating outward as a gas, it convects like a boiling liquid beneath the surface. The turbulent, bubbling motion is visible in the granular cells of the photosphere. Sunspots, regions of intense magnetic fields, appear on the surface, disappear in a few hours, or grow and persist for months in a mysterious 11-year cycle. The sun rotates once in 27 days. Because its equatorial regions rotate faster than the polar caps, the shearing action in the gas contorts the magnetic field into tangled structures which give rise to the sun's eruptive action. Shaped by these magnetic fields are the spectacular prominences, titanic streamers of gas reaching heights of more than 500,000 miles above the surface. The greatest explosions in the solar system are flares, intense bursts of light erupting with the force of billions of hydrogen bombs. They move at hundreds of miles a second. Then, after minutes or hours, they fade away. The dark areas across the solar disk are coronal holes, which may provide new clues to the sun's interior, and may be a source of the solar wind that blows outward to the farthest planets. On Earth, effects of these solar events are visible when auroras light up the dark Arctic sky and radio communication is disrupted. The sun is an average, middle-aged star. Yet it will generate heat and light for billions of years to come, as it has for 5 billion years past. It dominates the motions of all bodies in the solar system.
Parts of that film are based on facts gathered during the 3 Skylab flights. The 3 Skylab missions of the 1970s gave us more knowledge of our sun than in all the previous history of humankind. Several telescopes were mounted aboard Skylab. The last crew of 3 men spent almost 3 months in space, much of that time observing the sun and making thousands of pictures. Here's another clip from the Helios film.
NASA recently took solar research a long stride forward with its Skylab program. From its spectacular touch-and-go mission in June 1973, Skylab returned 25,000 unique portraits of the sun. Scientists estimate that the sun will burn for another 5 billion years. Its energy is created through nuclear fusion, but little else is known about the sun's surface. Solar research is vital to our control over physical conditions on this planet. A better understanding of the sun can help us cope with its menacing and dangerous aspects. During solar eruptions, compass needles on airplanes may swing erratically. Ship communications could black out. An ability to predict such eruptions would help prevent many tragedies. Storms, tornadoes, and hurricanes could be anticipated if we understood what is happening on the sun's surface. The Helios mission is an important advance in the exploration of the sun's activity.
The results of Skylab came to us because telescopes and other instruments were carried above the Earth's interfering atmosphere. Many of the observations of the sun made from Skylab are impossible to make from the ground because observation in parts of the spectrum is not possible. Dr. Richard Taussig explains an instrument called a spectroscope, which was used by Skylab's astronauts to dissect the sun's ultraviolet light for study.
Here's a small sample section of 3 of the spectra. On this scale, the whole spectrum would be about 100 feet long. This instrument is so powerful that it can separate nearly 100,000 different ultraviolet colors. Just what do all these black line images mean? Each atom produces its very own combination of spectral lines, just as each one of us has his own very special set of lines on his fingertips. So, if we have a complete list of atomic fingerprints, and we do have a tremendous data file on atomic spectra, we can tell exactly what atoms are present. More yet, by studying the intensities of the lines and their widths, we can say what the conditions were at the place on the sun that the instrument was observing. We can calculate the temperature and the density. We can make a chemical analysis, and we can even derive the velocities of the atoms. This is what the sun looks like in the extreme ultraviolet, and it is what the astronaut will see produced on his scope by the closed-loop extreme ultraviolet TV monitor that forms a part of the B instrument. The spectrograph slit is very tiny, something like this little red sliver, if you can see it. There are all sorts of different features and phenomena on the sun's disk, and above its limb in the corona. These regions are the active areas which are the spawning ground for solar flares. We can place the slit here, move it around, explore the structure of the region, and we can hope to be lucky enough to catch a flare. Or we can slew the ATM to point at this curious bright ring that surrounds most of the sun and study the conditions at the limb. By moving the slit out, we can investigate the changes in the sun's atmosphere at height intervals of about 500 miles, much as the meteorologist studies the Earth's atmosphere with sounding balloons. Why do we want to do all this? Because we still do not understand very well how the tremendous energy of the sun escapes. The outer sun's atmosphere, or corona, has a temperature of 1,000,000 degrees, but inside the corona, the edge of the sun is at only 4,000 degrees. We all know that heat flows from hot to cold, never from cold to hot. Even more mysterious and closer to our lives is the solar cycle. Happily, the sun is almost absolutely constant. But in the extreme ultraviolet and X-rays, the part studied by Skylab, it is anything but constant. In X-rays, every 11 years, it goes from almost nothing to very great intensities and back to nothing. It is certain that the solar cycle has controlled the Earth's climatic changes from prehistoric times. Many of us think it has a lot to do with our monthly weather. In any case, the sun is the object that is most important to life, and we must learn all we can about it.
Dr. Towsey also described some of the early results of Skylab, just a few of the thousands of facts gathered.
In the corona, the sun's disk is dark, with most of the emission above the limb. The active regions on the disk itself show all kinds of fantastic forms, but loops are still present, and it is clear that magnetic fields extend way up into the corona.
The large amount of information gathered during the Skylab mission is still being analyzed by scientists and astronomers. Hundreds of articles have been published in the scientific journals. Pictures tell us the story in a simpler way. In its quiet times, the sun is far from calm. It is a churning ball of hot gases. Its surface has bubbling granules. Sunspots come and go. During its quiet periods, observations from Skylab and the ground led to a better understanding of the solar atmosphere, temperature, density, chemical composition, magnetic fields, and physics. From analysis of thousands of pictures of the sun taken in the ultraviolet spectrum, we have gained new insights on how wave energy is transmitted upward to heat the outer layer of the sun. Ultraviolet pictures were processed to color code differences. Green shows part of the sun called a chromosphere with temperatures of about 35,000 degrees Fahrenheit. Red reveals the hotter part of the chromosphere, which is almost 270,000 degrees Fahrenheit. Blue shows us the corona with temperatures around 2.5 million degrees Fahrenheit. The poles of the sun were found to be different from the rest of the star. At the poles, the solar atmosphere is stretched upward, and there are long-lived holes in the corona. At these holes, the sun's magnetic field is relaxed, and solar particles of the solar wind can flow easily into space. That the coronal holes are clearly the source of solar wind disturbances was an important finding. The solar wind affects the Earth's upper atmosphere. Changes in the upper atmosphere affect radio communications as well as weather on Earth. Like scattered jewels, bright points of light dot the solar disk in this X-ray picture. Scientists checked magnetic maps of the sun and found that the bright points overlie compact magnetic regions that have both positive and negative polarity. About 100 of these bright points can be seen at one time on the sun's hemisphere, and they come and go at about 8-hour intervals, though some last longer and others are gone in a few minutes. X-rays are emitted by the sun's high-temperature gases, so only the hot corona is seen. Almost 60,000 X-ray pictures of the corona were taken. Scientists learned that the corona is built entirely of magnetic loops and arches. Cloud-like extensions of the chromosphere are called solar prominences. They are associated with magnetic fields on the sun's surface. These long ribbons persist for weeks or months before fading. The sun's outer atmosphere, or corona, reaches out millions of miles. One of Skylab's telescopes masked the sun's disk, creating artificial eclipses. 8 months of eclipse observation were done by Skylab as compared to less than 80 hours observed from all the natural eclipses since the use of photography began in 1839. The outer corona was found to be constantly changing. The sun is a seething inferno. There are huge eruptions and explosions. All this Skylab showed us in detail we had not seen before. Immense clouds of coronal material, called transients, are propelled outward by flares and prominence eruptions. The sun can have violent periods. We learned a lot from Skylab, but we still have much to learn about the star that keeps the Earth alive. In 1986, NASA plans to launch the International Solar Polar Mission. The shuttle will carry the Lewis Centaur rocket into low Earth orbit. The Centaur will ignite, sending the probe to the sun. The objective is to learn more about the Sun's polar regions and the space around them. As we saw, the polar regions are the source of the solar wind, which affects radio communications and the weather. Man shall continue to study the sun because his curiosity is insatiable, and because we are of the sun. Without it, we would not exist, and we must understand how it affects our weather, our communications, and our destiny. That brings us to the end of our first episode, Our Star, the Sun. Next time, during this 13-program journey through the solar system, we will preview the planets and examine in detail Mercury, the planet nearest the Sun. This is Larry Ross saying goodbye from NASA's Lewis Research Center in Cleveland, Ohio.